In Chapter 2, we start out with a description of atomic structure. So an atom has three types of particles, and these are the proton, neutron, and electron. There are other types of particles, but these are the three that are the most important for biology. So the proton has a positive electric charge. The neutron has no electric charge, so it's electrically neutral. And the electron has a negative charge. The protons and neutrons are located in a dense nucleus in the center of the atom, and the electrons orbit the nucleus. This is a helium atom. It is not drawn to scale because the nucleus is very, very small and the orbits of the electrons are very large. And our textbook says that in order to draw the atom to scale, the nucleus would have to be the size of a pea, and the orbits of the electrons would be the size of a baseball stadium. So there's a lot of empty space between the nucleus and the electrons in each atom. Another thing about atoms is the atomic number. So the atomic number is the number of protons in the atom of a particular element, and this is fixed for each element. If you look at the periodic table of the elements, you can see that for each element there's a number. So hydrogen has 1, helium has 2, then lithium is 3, beryllium 4, etc. Boron 5, carbon 6. These numbers are the atomic numbers. So these are the numbers of protons in the nucleus. So an element is defined by the number of protons. And however, the number of neutrons can vary somewhat. So, for example, for carbon, there's 3 different forms of carbon in nature. They all have 6 protons because that defines carbon, but they have different numbers of neutrons. And so we call these isotopes, different forms of an element with different numbers of neutrons. So the most abundant isotope of carbon is carbon-12. It has 6 neutrons. But there's also carbon-13, which has 7 neutrons, and carbon-14, which has 8 neutrons. Some isotopes are very useful in medicine and for medical diagnostics, and also for research, and also for dating of fossils and other artifacts. And although some isotopes are radioactive and dangerous, others are not dangerous, even though they do have radioactive decay, such as carbon-14. Carbon-14, although it does decay radioactively, the energy released when it decays is very, very tiny. And so it's not dangerous at all, it's harmless. And in fact, at any moment, there are many trillions of carbon-14 atoms in our body. For each isotope, there's a mass number. So the mass number is the number of protons plus the number of neutrons. So each isotope has a unique mass number. And for example, carbon-12 has 6 protons and 6 neutrons, and so its mass number is 12. And next in the chapter 2, there's molecules and compounds. So what are molecules? Molecules are atoms that are bound to each other through a chemical bond. So two or more atoms bound together. And a compound is the binding of different elements together to form a molecule. So molecule is a kind of more general term. Compound is a molecule that has different types of elements in it. And in a compound, the proportions of the elements are fixed. So for example, in water, you have 2 parts hydrogen to 1 part oxygen. Next, we have the arrangements of the electrons in atoms. And the electrons in atoms are arranged in shells. So these shells have certain amounts of electrons that can occupy them. So in the first shell, you can have up to 2 electrons. This little dot in the center is the nucleus. And then you have the first electron shell. The second electron shell can hold up to 8 electrons, and the third electron shell can hold up to 8 electrons again. So next we have valence. Valence is the number of electrons, if gained, will fill the outer shell of an atom. And this is important because it determines the chemical properties of an element. So for example, carbon has 6 electrons, and so it has 2 in the inner shell, and then in the second shell has 4. So this means that there are 4 empty spaces in the outer shell of electrons. And so carbon is said to have a valence of 4. This means that it has a tendency to pick up 4 more electrons through chemical bonding. And there are 3 types of chemical bonding that are important in biology. They're the covalent bond, ionic bond, and hydrogen bond. Okay, now let's look at covalent bonds in more detail. So covalent bond, in a covalent bond, 2 atoms share a pair of electrons. So for example, hydrogen will tend to form molecules consisting of 2 hydrogen atoms. The 2 hydrogen atoms are bound by a covalent bond between them. So normally a single hydrogen atom has a single electron because hydrogen has 1 proton, so it has 1 electron to balance the charge of the 1 proton. But if hydrogen gains 1 electron, then its electron shell is filled, and that's very stable, and so hydrogen will tend to form this covalent bond in order to get that fully filled electron shell. Notice that if 2 hydrogen atoms share an electron pair, they both have a filled electron shell with 2 electrons. Another example is molecular oxygen. So oxygen in nature is a gas that is O2. So there's 2 oxygen atoms bound to each other by, in this case, 2 covalent bonds, or called a double bond. So why is there a double bond between 2 oxygen atoms? It's because oxygen normally has 8 electrons, and it has these electrons arranged so that 2 are in the inner shell and then 6 are in the outer or valence shell. Notice that if oxygen gains 2 more electrons, it'll have a completely filled valence shell. And so oxygen tends to form bonds in which it gains 2 electrons. So for the molecular oxygen, here I've shown 2 oxygen atoms bound to each other by the double covalent bond. You'll notice that the oxygen on the left, I've indicated its electrons in red. So you have the 2 electrons in the inner shell, and you have the 6 red electrons in the valence shell. And the oxygen atom on the right has its electrons in black. So it's got the 2 inner electrons, and then it has 6 in its outer shell. If they share 2 pairs of electrons, now each oxygen atom has 8 electrons in its outer valence shell, and that's a filled shell, and that's very stable, and so they tend to do that. You can also have covalent bonds in compounds. So for example, water consists of H2O, and in water the oxygen has a covalent bond to one hydrogen and another covalent bond to another hydrogen. So if we look at the electrons, you can see that the oxygen has the 2 electrons in its inner shell, and then the 6 in its outer shell. And if it gains 2 more electrons, it has a filled valence shell. And for the hydrogen, it has 1 electron. If it gains 1 more electron, it has a filled shell. And so the electrons of the hydrogen are shown in red, and the electron from the oxygen is shown in black. So now you can see that the oxygen has gained 2 electrons by sharing them with the hydrogens, and the hydrogens have gained an electron through sharing it with the oxygen. So now all of them have filled electron shells. So you can have these covalent bonds in compounds. The next type of bonding is called ionic bonding. And in an ionic bond, instead of sharing electrons, an electron is transferred from one atom to another. It's not shared, it's transferred completely from one atom to another. So an example is sodium chloride, or table salt. In sodium chloride, the sodium atom normally has 11 electrons. It has 2 electrons in its inner shell and then 8 in the second shell. And it has a single electron in its outer valence shell. Chlorine has 2 electrons in an inner shell, and then 8 in the second shell, and then 7 in its valence shell, for a total of 17 electrons. Notice that if chlorine gains 1 more electron, it'll have a completely filled valence shell. And if sodium loses 1 electron, this valence shell will disappear, and the shell interior to that is filled. So sodium will spontaneously donate that outer electron to chlorine, which will readily accept that electron, because then they have these filled valence shells. And when that happens, though, the sodium now has a deficiency of electrons. If it donates this electron, now it only has 10 electrons, but it still has 11 protons. And so it becomes positively charged, because there's a net positive charge there that isn't balanced by the electrons. And the chlorine, because it gains an electron, it has 17 protons but 18 electrons when it gains one electron. So when that happens, the sodium becomes an ion. It's now a positively charged ion, and the chlorine is a negatively charged ion. And so these ions bind to each other because of the opposite charges on the ions. So that you have an ionic bond. So it's the electrostatic attraction of these two ions that holds them together. That's a form of bonding. And the third type of bonding is hydrogen bonding. Hydrogen bonding involves atoms that are electronegative, such as oxygen or nitrogen. These atoms have a tendency to pull electrons towards them when they're in a molecule. So for example, in water, you have H2O, and the hydrogens are on one side of the molecule, and oxygen is on the other side of the molecule. And oxygen, being highly electronegative, pulls the electrons towards it. And so in the water molecule, there's an uneven distribution of electrons. So you have more electrons on one side of the atom and less on the other side. And this is called a polar covalent bond. You have the covalent bond, but because of the electronegativity of the oxygen, the electrons tend to be on this side of the molecule. And the effect of that is that when you have many water molecules, the hydrogens will hydrogen bond and form this kind of bonding with the oxygen, because the oxygen is more negative. And so you have a kind of electrostatic interaction between the electronegative oxygen and the hydrogens, which are not electronegative and tend to be slightly positively charged, and the oxygen slightly negatively charged. So there's an electrostatic interaction there. And the hydrogen bonding, each hydrogen bond is not very strong, but when you have many molecules, the effect of each hydrogen bond is additive. And so many water molecules together will have an additive effect of their hydrogen bonds adding up to a fairly strong interaction of the entire group of water molecules. Next, we have the life-supporting properties of water. There's 5 of these, and I'm showing the first 3 here. So the first one is called cohesion and adhesion. So water molecules, because of their hydrogen bonding, tend to stick together, and that causes the surface of water to have an unusually high surface tension, and this is important for water. And it also allows adhesion. So adhesion is the sticking of water to other polar substances, and this is very important in plants where water is transported up the plant from the ground through thin tubes that are thin enough that there's capillary action through the tube because of the adhesion of the water to the polar walls of the tube. Now, the second one is evaporative cooling. So evaporative cooling, this is how animals and plants can cool themselves down when they get hot. So in animals there's perspiration, which is water evaporating off the surface of the animal's skin. And in plants it's transpiration, and this is water evaporating off the leaves of the plant. And the reason that is possible is because when you take liquid water and you add heat to it, it can go from the liquid state to the gaseous state. But it requires heat for that, because the hydrogen bonds would otherwise keep it in a liquid state. But the added heat will break the hydrogen bonds and allow the water to go from liquid to gas. And that removes heat from the body. And so has a cooling effect. And the third is the fact that ice, when it is a solid, it floats on top of the liquid ice. So water has an unusual property that it's less dense in the solid state compared to the liquid state. So this is because in the solid state, when water freezes and becomes ice, the hydrogen bonds elongate and become longer and more rigid, and that separates the water molecules from each other more than they would be in the liquid state, where the hydrogen bonds are constantly forming and breaking. And so this means that water in the solid state, being less dense, will float on top of liquid water. And so this is important for aquatic environments, where in the winter the surface of the body of water will freeze and the water underneath will be insulated by the layer of ice on top. This would be true for lakes, ponds, also ice sheets where glaciers flow into the ocean. And the last two properties of water that are important to life is that water is a good solvent. So water, being a polar molecule, can dissolve other polar molecules or charged molecules, and many of these are important for life, such as sugars, which are a source of energy, and salts and acids, which are important for metabolism. And so water is a good solvent, or a good environment in which to have those molecules dissolve. And the last property is that water will spontaneously ionize, but it does so to a moderate extent. So water, a small portion of the water, if you have pure water, a small portion will break down into hydrogen ion and hydroxide ion. But it does this only to the extent of 10 to the minus 7 mole per liter, or in other words, 1 over 10 million mole per liter, which means just a very small portion of it is ionized. And that's important because the amount of hydrogen ion can, if there's too much, that can be damaging. Also, if there's not enough, that can also be damaging. So if you have too much hydrogen ion, it can damage proteins and other molecules that are needed for the cell to function properly. Finally, in chapter 2, we have the pH scale. So what is pH? pH is defined as the negative logarithm of the hydrogen ion concentration. So this H plus in brackets means the concentration of hydrogen ion, the amount per a given volume. When you have pure water, the hydrogen ion concentration is 10 to the minus 7 mole per liter. And so if we take the logarithm and put a negative sign, then we're just taking the exponent and we're changing the sign of the exponent. And so the pH of pure water is 7. And that pH is in the middle of the pH scale. The pH scale goes from 0 to 14. And pHs that are below 7 are called acidic. So acids have a pH below 7, and pHs above 7 are called basic. So bases have a pH greater than 7. And this is because acids donate hydrogen ion to a solution. They will give off hydrogen ion if they're added to water. And so that means that there's more hydrogen ion, and so as you have more of it, this exponent gets lower. And that means more hydrogen ion, because it's a negative exponent. And the base removes hydrogen ion. So the base will take it away, and then that makes this number smaller, larger, makes the exponent larger. So let's look at a couple of examples. On the one hand, you have, if you have a pH of 1, what would that mean? So pH of 1 would mean 10 to the minus 1 mole per liter. That's 1/10 of a mole per liter, 0.1 mole per liter. And that's a huge amount of hydrogen ion. That's the pH of battery acid. And then towards the other extreme, you have something like bleach, which has a pH of 12. That's 10 to the minus 12 mole per liter. That's a very low number. That's 1 over a 10, 1 over a 1 with 12 zeros after it, or 1/trillionth of a mole per liter. So that's a very small amount of hydrogen ion. So we have this relation then where when the pH goes down, hydrogen ion concentration goes up. So, for example, the battery acid has very low pH and has a lot of hydrogen ion per unit of volume. And conversely, when you have pH goes up, the hydrogen ion concentration goes down. So in bleach, it has a high pH and has low concentration of hydrogen ion.